So now we'll stop all of this and let's discuss. For those of you who have never seen that, I think it's very important to discuss what is the Ito calculus, because it will allow us to define different types of stochastic integrals that we haven't much discussed so far. And it will allow us to derive what is called the Fourier-Planck equation and the mean first passage time equation, from which we can do all the calculus. Okay, so the essence of this is the following example. So if you have, again, x1 and x2, this is two deterministic functions. You know, by definition, if they are regular, the regularity is good enough, that dx1 x2 is x1 dx2 plus x2 dx1. But this is not correct if x1 and x2 are two stochastic processes. So I'll give an example that we'll do together, and we will start from there. This is b delta t plus a1 dw, and I'll take dx2, which is b2 delta t plus a2 d omega, and this is the same omega here and here. And those are constant, a1, a2, b1, b2. All right, so I want to take this to calculate this quantity, x1, x2, and this quantity, and I would like to compare to see where the difference comes from. Okay? So let's do the calculation. We can integrate this, right? So what it gives the following. x1 is just b1t, because those are constant, b1t plus a1w plus alpha 1. You see, this is x1 of t, x2 of t, which is b2t. So again, you do it for yourself, and you make sure that I'm doing things correctly. a2 omega plus alpha 2. Now I can calculate x1, x2, and differentiate. All right, so let's do this. x1, x2 is the product. So this is alpha 1, alpha 2. Now we have to calculate. So the term in omega is a1 alpha 2 plus a2 alpha 1. Now the term in t, or in omega squared. In omega squared, you get what? In omega squared, I think we have only one, correct. a1, a2 omega squared plus the term in t omega that comes from here. So this is b1 a2 plus a1 b2, and this is t omega. And then there is a term in t squared, which is b1 b2 t squared. So we need 9. We're missing which one? Omega, t omega. T is missing, right? Yes, that's good. So this is b1 alpha 2 plus alpha 1 b2. That's it. And now let's differentiate this d of x1, x2. Right? You're saying that I'm completely stupid, you know, I just integrate and I have to differentiate. But it's okay, because I want to calculate the difference. Okay, the differentiation of a constant, this is a constant. The differentiation of d omega, this is a1 alpha 2 plus a2 alpha 1 d omega. Then this is plus a1 a2 d omega squared. This I don't know what it is, so I leave it this way. I don't touch. This is, again, I don't know what it is, b a2 plus a1 b2 t of d omega This I know because b1 and b2 are constant, and this is just 2b1, b2 t. You differentiate this. And this is also known because this is b alpha 2 plus alpha 1 b2 dt. All right? I haven't made anything yet. I just wrote this d, and now we have to understand what is the meaning of this d. Okay, so to calculate, to understand the meaning of this, I would like to go back to what we discussed. So how are we going to calculate d of omega, d omega? And for this, we need to look at this more carefully. Again, this is now some mathematical treatment that we have to understand. What is d of omega squared? And for this, I'll propose to compare this. Basically, we would like to compare this with omega d omega, right? And so to calculate this, we can also compare the integral of the function. So I can integrate this or integrate this to compare them. So I'm interested now in calculating integral from 0 to, let's say, capital T of omega of s d omega of s. And for this, so to calculate this, to compute this quantity, let's call it let's call it s of t. To compute s of t, we will start as we did last time. We will introduce the sum tn, which are the sum from 1 to n of the like Riemann sum, if you want, of this quantity. So now we decompose 0t, the time interval from 0 to t, into segments of the same delta t. So we go from, let's say, t0 to tn. So we sum from 1 to n, and so we have omega of tk, omega of tk plus 1, minus omega of tk. Now, what can you say about this? So this would represent the discretization of this. D omega, this is the discretization in this interval. And this, I choose omega tk, which means I choose to calculate. So suppose you have a function. So you discretized it. So this is your time interval. This is now Brownian motion. Take the difference between these 2 points. And this is tk. This is tk plus 1. I choose here omega tk. Now this is a choice. You can approximate a function, and it doesn't matter in Riemann or any kind of integrals, the fact that you choose here tk or anything in between. But for the stochastic processes, it does. And this is very important because this is a source of many confusion in stochastic processes. It's very important to understand that you have the choice. And now the question is, what is a physical choice? Are all the choices physical? So the answer is no. Here there is a choice, and it's very important. So if you choose here this is called Ito calculus. You could choose here omega tk plus 1. Right? This is if it was a purely deterministic function, And if this is a Riemann sum, if you take k goes to infinity, it converges to the classical integral. Here, it's not going to be the case. And this, so this is the choice, 1. And this choice, if you take this instead of this is called the Stratanovich calculus, Stratanovich form. The paper. This is called the Stratanovich form. And you can also have any, you can, if you think about any convex combination, it's S omega tk plus 1 minus S omega tk plus 1. So for example, for S equal 1/2, you have also a form which is which actually gives the classical integral. Now, which one is the correct one? What? Stratanovich? Why?
It's not anticipating?
The one it is not anticipating is this one.
Yeah, yeah.
So this is exactly the response. This is because it's not anticipating, it doesn't see the future. But sometimes in signal processing, you see this form. Why? Because if you have a radio signal that you have acquired and you process it, you know the future. And it can come out that you end up with a Stratanovich form to calculate things. Because you know the future. Okay? So people did not abandon all of this, but I want to mention that to you. This is in books. This is discussed in length in books and in papers. And it's even not clear in papers why people are applying Stratanovich form to physics problem. But it is done. Now you have to understand what's the origin of this. Okay, so now we are left here. Now let's do the calculation with this, and at home I'll leave you this to do. Now let's start the calculation. Can we calculate Tn, which is, so you have your Brownian motion multiplied by this quantity. Can we rearrange this? The answer is yes. We are going to do that now. Tn can also be written as a difference of squares. So this is omega, let's write it, omega k plus 1, tk plus, okay, let me not define omega k as omega of tk, right? So I'm not going to repeat all of this. So omega k plus 1 squared minus omega k squared. So if I do this, I am left with 1 minus omega k squared divided by 2, so that it is minus 1. We are left with omega k plus 1. And we have introduced this term, so we have to remove this term. So this is omega k plus 1. Somebody has to check, right, that I'm not doing a crazy thing. Omega k squared divided by 2. Now, omega k plus 1. Is that correct? This cancel with this one. This plus this equal minus omega k, which is this one, and this is just this one. That's it. Okay? So this is the sum. So if you sum this is a telescopic sum, everything will cancel out. So it should be omega squared t divided by 2 minus omega of 0 divided by 2. And this we are left with omega minus, so this is minus all of this. So this should be 1/2 omega k plus 1 minus omega k squared. From k equals whatever, from 0 to n minus 1, something like this. Or to n, Tn. Okay, are we good? Is it correct? Yes, this is correct. So when n goes to infinity, what is the... So let's assume, for simplicity, this we can always assume, because this is defined up to a constant, that this is constant is 0. I don't care. Now, what is the limit of omega squared t when n goes to infinity? Where is n here? Do we see an n? There's no n. So the limit is this. Okay, so this we know. So we have a sum of Brownian motion, and we're trying to study a limit of sum of Brownian motion. The question is, what are we talking about here? Where is the limit, where it goes? Now here comes an interesting question. So this is n goes to infinity, so we refine the steps n going to infinity, and we have found that in the limit in the space of non-anticipating function, as you mentioned, Tn, as n goes to infinity, is going to, the limit is this integral. So if we can calculate this, we will know how to calculate this. So we have this now, this expression, and now we would like to look at the limit when n goes to infinity. So we're left with this term. What is the limit of this difference? We have now a sum of Gaussian. What is the limit when n goes to infinity of this? I mean, the first question is, does this have a limit? You see, you are summing an infinite number of Brownian motion squared. So who knows? This is called the... What is... Okay, when you have a sum of random, of identically distributed variable, you have A, they are identically distributed, and you look at the sum. Let's go to the basic things. So those are Brownian motion. I mean, those are stochastic variables. They are random variables. Suppose all of them are independent, identically distributed. Is this sum, if it converges, where it should converge? To which number? To which? Oops. Yeah, I cannot move this one.
Isn't it equal to the square root of n times the Gaussian variable?
Yes. Okay.
If the mean is 0.
If the mean is 0, but if the mean is not 0?
The mean times the number of variables plus correction, the other square root of n.
Okay, so then the thing we should anticipate for here is to first try to calculate the mean of this quantity. Is it finite? And if it is finite, to look at if this number, although they are random numbers, when n goes to infinity, possibly they will select the mean value, and this will be the limit. Okay, so let's look at this question. What is the mean of this variable? Is it finite, and what it is? And then we will proceed. So why is it important to manipulate correctly Brownian motion and all of this? Because if you do some simulations, or if you want to analyze things with noise, correlated noise, of all kind of noise, you have to usually look at this quantity, how they are transformed into transformations. And you should not be afraid of doing the calculations. This is why I do all the calculation on the board. It's not that I could say, okay, you do your calculation at home. You should see all of this so that you should not be afraid yourself of repeating all of this. Okay, what we were discussing is the expectation of Tn. So who can tell me what is the expectation of Tn? All right, so let's just replace. This is 1/2 of the sum of the expectation of omega k plus 1 minus omega k squared. So this is what we have studied at least 3 or 4 times. This is simply this is a Brownian variable of increment delta t. This is exactly what we said. Tk plus 1 minus tk is delta t. So this is, okay, let me write it this way. This is tk plus 1 minus tk. Let's assume this is of d. The diffusion coefficient here is 1. I mean, I don't, so that maybe 1/2. Yeah, what is necessary to have this? Right, I didn't tell you that this omega k here is characterized by a variance. I assume it is 1, so that... all right, so then we have to sum this from 1 to n with 1/2. And this is equal to what? Simply t divided by 2 now. All right. Now suppose, let's accept this result for a second. Suppose I'm proving it. I will show that then what we need to prove is we need to show the convergence of this towards the mean. And we will show this the convergence in probability. But let's suppose we have this for a second. Then what do we have? We have the Tn. So suppose we have the proof. Tn would converge to omega squared t divided by 2 minus 1/2 of t. And now, which means S of t, because this is a convergence, and this is, by definition, this is a limit. So we have integral from 0 to t of omega of s d omega s equals omega squared t divided by 2 minus t divided by 2. Right, this is a result in limits. This is whatever it is, and this is the limit of what we have seen, of the Tn, which is this. Now you can differentiate, or you can write this with the infinitesimal version. So integration of 0 to t dt of this so we can rewrite this as omega t d omega t equals d of omega t that we didn't know what. So let me multiply everything by 2. Just multiply by 2 minus dt. So I'll take the dt, I'll put it there. So this is plus dt. And now this is exactly what we didn't know, what to calculate here. You remember we said this, and now this is not the classical term, which is 2 omega d omega. This is 2 omega d omega plus dt. Okay? And so this, you'll start to see the difference between the classical calculus and the new Ito calculus. This is where it comes about and how it propagates. Because now, so you can have this, will give us, so 2 omega d omega minus, no, plus dt. So here, actually, what you can prove, I'm not going to show it. This is t d omega plus omega dt. We can show it the same way that I have shown this. You have to calculate the, you redo everything, and you, instead of calculating omega d omega, you take t this, and you can redo all of what I have done, and you'll be able to show this. So ultimately, what is missing here when I have these stochastic processes? The only difference, this is not going to change if you multiply x1 dx2 or plus x2 dx1. This is going to be the same. This is the same because this is the same calculus. So the only difference is going to be here, delta t. So what is the difference? We can write it this way, dx2 dx1 plus x1 dx2. So d of x1 x2 equals this plus a1 a2 delta t. Okay? This is for omega, a Brownian a process of variance 1. Okay, so now we have assumed this. Now let's prove it. All right, so now we have this quantity. We assume that if this is correct, we plug that into this. So now we have to prove that what? We have to prove that Tn converges to, so what you said was the large number theorem where this mean is 0. But now when it's not 0, we have to, it's much more simple. So let's prove that Tn converges to the expectation. And how do you show that? We want to look at the difference, Tn, minus the expectation. And we are going to prove, you are going to use what is called the classical theorem. This is maybe the only time where I will use something of classical theorem. You have to use the Chebyshev inequality, which give you an estimation when you have a random variable minus the expectation. This is larger than epsilon. This can be estimated by the variance, which is the expectation. This is less of Sn. So why I wrote here S1? Okay, this is Sn. Sorry, this is Tn. Okay, let me write it this way. This is Tn squared divided by epsilon squared. So it goes like this. So this is called the Chebyshev inequality. This is classical. Not going to prove it. So it says that for any epsilon positive, if you have a random variable x, the probability that x minus the mean of x, this is larger than epsilon, this is less or equal to the variance sigma squared. So sigma squared means expectation of x minus the mean squared divided by epsilon squared, which is finite. I assume that you know, we assume that we have finite variance. And so this proves that if we can show that this goes to 0 when n goes to infinity, if we can demonstrate this, this will show that we'll have in probability that almost everywhere the limit of Tn is the mean. And this is what we wanted to prove. All right. So what is now, we have to calculate what is the this Tn minus the mean, so the expectation of this. All right, this is what we are left with. So let's prove that this goes to 0 as n goes to infinity. All right, so sigma n, let's call this sigma n squared. Sigma n squared is the expectation of Tn. So this is, so this can be also written expectation of Tn squared minus expectation of Tn everything squared, right? Because you have the squared here. So this is, I put it square, so Tn squared minus the product twice Tn multiplied by this, and you take the expectation of this, plus expectation of Tn squared, so you are left with this one, right? You double check everything. So all right, this is what we get, and now we need to do this calculation. So this is the sum of what? This is the expectation of the sum. What is this Tn squared? Yeah, this is correct. So this is d omega k squared minus the expectation of Tn, which is the sum of d omega k, sum of d omega k, this, yeah, with a squared here, everything squared. I just introduce in here what is the definition of Tn. Okay, and so now what do we have here? Okay, so this squared, I can also develop it. So this is the sum. The first one is a sum from 1 to n of k and q of what? Of d omega k squared d omega q k squared. And now we have the expectation of this. Is this correct? Yes. I just take it squared, put it twice, and use as we have already done before. And this term, this is minus the sum of, again, the same quantity. This is the expectation of the same, but except now we have the expectation of d omega q squared, expectation of d, sorry, it's omega k squared, and again k and q. And this, so for example, what happened when k equals q? Now what happened when k is not equal to q? Those are independent, so this should cancel out. So we are just left with what happened for k equals q. And we can always then get, because this is a minus, this is always less than the sum for k equals q of this squared, which is expectation of d omega k or q, it's an important, power 4. From q equals 1 to n, or n minus 1 or n plus 1, I forgot. So now we are left with this sum to calculate. And now for this we are going to use the expression of the Brownian motion, and that will be the end of this calculation. So now what is this sum? So first of all, this sum is the same because we have n independent Brownian variable. So if they are all independent, this sum can be seen as n time the expectation, let's say, of the first one. It's an important, of d omega 1 to power 4. So now what is the expectation of d omega 1 to power 4? And then there is an n that we are not going to, we should not forget about this one. So what is this? So this is the probability distribution. This is the expectation of this variable. So we need to have the probability distribution function during time step delta t, and we have to integrate x to the power 4, p of x. You have to integrate, let's say, from minus infinity to plus infinity. This is by definition the expectation of this variable. Is that correct? Yeah, something like this. Right? We are in dimension 1. So we said that, you know, all the increments here are all independent. That's why I used the first one, delta t. So this is the transition probability. This is transition probability for a Brownian variable during time delta t. Condition that at t equal 0, it was in 0. This is what we said, omega of 0 is 0. So then this is what? This is, in dimension 1, this is 1 divided by 4 pi delta t. So we said diffusion coefficient equals 1, square root exponential of x squared divided by 4 delta t. And then we have to integrate dx, x to the power 4. And this is twice, because it's symmetric, from 0 to infinity. Now, this is what we need to calculate. Actually, we don't need to do the calculation. Yeah, and what is delta t? So delta t corresponds, n times delta t is the entire interval, which is capital T. So delta t is t divided by n. And so we are interested in the limit when n goes to infinity, right? So what we just need is to see the dependency in delta t, which will give us the dependency in capital T. Yeah, I'm sorry, I haven't... are you with me? Yeah, okay. Not hard. It's elementary calculation once we have cut it into small pieces. Okay, so now how do you do this? This is just the changing variables. U equals x divided by square root delta t. And what do we get from this? We get twice. So x to the power 4. So first of all, in the exponential, you get x. So this is u squared divided by 4. Dx is equal to square root delta t du. So you get square root delta t here, du. You have x4. This is square root delta t to the power 4, u4. And then we have to divide by how much? By 4 pi delta t. Right? Integration from 0 to infinity. And so we need to look at the delta t term. So this goes away, this goes away. This integral converges, and I don't care, I don't need to calculate it. And we have here delta t to the power 2, because we have square root and 4. Multiplied by a constant. I don't know what it is, and I don't care. And this is, so then, let me remind you that there was multiplied by n here, so I have to add the n, 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 n. So n times delta t is how much? It's t divided by n squared multiplied by constant, which is ultimately t squared constant divided by n. And this goes to 0 as n goes to infinity. All right? And I think we are done. This goes to 0. This goes to 0. This is the inequality. So this is okay, and this goes to 0 as n goes to infinity, which shows that in probability we have this convergence. Okay? So now, this is the understanding of what we are manipulating. When you manipulate the stochastic integrals, you manipulate the limit of Brownian variables. Each time you see this, you cannot decompose into a sum. This is what you have to do. You decompose into a sum, and then you analyze the sum. I'm giving you the conclusion about the way of thinking. Okay, so this is important because now you see when you have to calculate, and this is the next thing we are going to do. if you need to calculate a function of a Brownian motion, we'll have to pay attention to the fact that the derivative, for example, what is the derivative of a function that depends on x? So suppose you are looking at the f is the mean first passage time. It gives us the, then if you need to calculate quantities, we have to pay attention because of this propagation of the Ito calculus. Okay? Okay, let's do 10 more minutes and then you are free. Again, this is textbook, I'm sure. But if you haven't seen, or if you have seen version where you manipulate Grunwald inequality, and from a mathematical point of view, I'm not sure you get the spirit of where we are going. You understand how to manipulate things, but it's important to understand the where we are going with all of this, and where the terms are coming, why we do this approximation, when things are coming from the physics, when it comes from the mathematics, when it comes from the stochastic processes, to divide in your head, you know, where things are coming from, so that when you find a new problem and you model it, you have the tools to react. Okay, so this is done. This is finished. And now we can go to the hard stuff. So you can do at home. You can look at what the Stratanovich form gives. That is, if you have the Stratanovich, how this is going to be changed? Plus is going to become, that's right. Plus becomes minus, and if you are exactly at the in between, let's say you take the point in the Riemann, which is the average of the top of the, I mean at a point, the beginning minus the final point. What do we get instead of minus? So this is minus when we took, yeah, it takes 0, that's it. So this you have to show it for yourself. Yeah, and this is also important. This is the basis of, you know, when you do signal processing, when you do tracking of signal. Tracking of a signal is a problem backward in time. Because if you have a signal, for example, you know, you can go backward, so you have information about the future, but you want to use your information and all your signal processes, for example, to extract features in the signal. Of course, it's different if you have a radio and you have to denoise the radio at the same time the signal is coming, and then you have to, you know, how you do this denoising at a real time. And this, yeah, so there's all kind of algorithm, but I mean, I'm not going to present that this year. Okay, so now let's go to the next stage, which is called the full. I mean, there is other. Okay, I'll skip some exercises. Now let's go to the full Ito formula, which is the following. So Ito's formula. So if you have a stochastic process, you would like to calculate information about the stochastic processes, like what is the mean, what is any moment of interest, conditional information, what is the probability to find the particle outside, knowing that it has hit something. So in principle, you would like to calculate, can we calculate for any function f you want, f of x of t? Basically, when f equals squared, I mean, I'm interested in this differential. We found it when f equal to squared. That is, f of x equal x squared. This is just what we did here. So now what is d of f of x for a general function f? Let's suppose f is sufficiently differentiable, at least 3 times, maybe less, I don't care, in a domain. Can we calculate this quantity and what it gives? So if you have a regular function, what do you get? What you get is d of x. If you have a stochastic process, which is, let's say, x dot equal b of x, so you have along a dynamical system, so you have to differentiate with respect to your field. This is df dxi at position xt, right, multiplied by dxi, which is here bi of x of t delta t. So this is the from, let's say, if you are in dimension n, so omega is a, let's say, any kind of domain in n dimension, dimension 2, 3, 4, whatever. So that's it. This is the linear. This d of f, this is called the linearized form, and that's it. And the rest you have term of dt squared, which I don't care. What do you get now for Ito calculus? What do you get for a stochastic process? Instead of having x dot equal this, now I'm interested in x dot equals b of x plus sigma of x w dot. So how do you calculate this when you have a Brownian process? A Brownian plus, I mean, a stochastic process. Okay. So we've done more or less everything. I will patch the important part. And this is called, the result here is called the Ito formula. And this is important because from the Ito formula, you can calculate, we will derive the mean first passage time equation, and the Fokker-Planck equation, and all of these important equations that then we can solve. So to do this, we'll do the same as before. You want to calculate f of x of t minus f of x of 0. So you have a stochastic process, and basically we decompose in time along the trajectory. So this is 0, this is x of time t. It has a deterministic element and stochastic element, and this will decompose by cutting into interval of size delta t. This is tk or ti, and this is ti plus 1, and this is f of x of time ta plus 1 minus f of x of time ta. So we look at, this is a decomposition into small increments. The difference between this and this is the sum of these increments. And now what we do is, let's look at dx. I'll write it this way. It's an important dx of dx. This is b of x delta t. So if we are looking at point, let's say ti, let's write it x of dx of I. This is by definition xi plus 1 minus xi, where xi is x of ti. So this is this difference. This is b of x at xi plus, so you can, there is a matrix here. This is called the tensor. Sigma of x at position ti, and now this is d omega I. So it's a little bit more complicated than this. Okay, so if we have in n dimension, B is a vector field. So this is B1, Bn. Sigma is a matrix, and omega is also a matrix. So omega here, this is n dimensional Brownian motion. This is the notation. Let's say we're in dimension n. Sigma is a matrix, so I'll call it sigma k q that can depend on x. So this is called the diffusion tensor. All right, so this in principle is the product of a matrix multiplied by a vector. Okay, and then so what we are going to do now is just use a Taylor expansion of this difference to order 2. Right, you have a function of b minus a. This can be written as a function. This is, so using the Taylor expansion, the first order term will give us df dxk at position xi multiplied by dxi, which can be replaced by this. And so this is b of xi delta t plus sigma. Now we have to be careful. So this is now d omega I. So now in terms of matrix, this is the coordinate k. So this is k, and then I multiply by q, and here I use the q term. Or I can write it, okay, I will write it this way. I will write it sigma. You see, this is, I take the coordinate, k coordinate here, and this is the coordinate k of this. Plus, so this is for dimension going from 1 to n, plus 1/2 of the sum of ddf dxk dxq of this k and q. So this is the same, bk of xi delta t plus sigma at position xi, sigma of position xi d omega I. So this is k, this is the k term, multiplied by the term which is the term q, qxi delta t plus sigma x. This is the part of the class which is the most boring. It will become much more interesting when it will be applied. But I have to go through all of this. If you don't do it, you will be always afraid of writing it yourself. So let's do all the, calculate. This math is about calculation. So sigma x I d omega I, and this is the matrix, the q component of this matrix, right? Which means we have to sum. This is later on the sum of all this vector multiplied by this matrix. Okay, and then plus something that is negligible. Plus delta t squared. I mean delta t, capital O of delta t. A little capital O of delta t squared. All right, so now what do we do with all of this? What is the term? So this is a stochastic equation. This is a stochastic equation. And so like this term, there is a term that is going to be dependent on delta t, and a term that is going to be dependent of the noise. Time, noise. So here we have to identify the same, to group what is depending on time and to group what is depending on the noise. So let's do this. Where is time here? The first term in time is in here. And where else? So where is the noise term? There is a noise in here. There's a time in here. And now we need to analyze this term, which is, let's suppose this is just dimension 1. Then we have here delta t multiplied by delta t. So this is delta t squared. Delta t squared go to the garbage. We don't care. Delta t multiplied by dq. This is exactly, you remember, this is exactly the calculation I have done here. except this was dimension 1. This is t multiplied by noise. And t multiplied by noise, it's really like this. And so basically, two order delta t, this is for delta t small. I mean, this is an integrated version. But here, this is delta t multiplied by d omega. So we'll get delta t multiplied by d omega, and we will see that this will go to 0. I mean, this is not going to contribute because of the Brownian motion. The expectation of this is 0. Okay, so now let's rewrite this in terms of time and noise. So this is a sum for I going from 1 to, let's say, capital N. And N will go to infinity. N here, little n, is the dimension of the space. So now this equal to this, and this here equals, so what is missing in here, this is a different, I've used Taylor expansion at each point. So now if I want to have this equal term, I have forgotten to use the sum from I going from 1 to n. Okay. So now, what is the limit when n goes to infinity of just this term here? Remember, so we cut, and we have applied the Taylor expansion. And now we are going to study each term separately. So what is the limit of this term? Yes, that's right. So I need to move on to the next board. Yes, that's right. This is exactly the integral of what?
Gradient of f.
Yeah. So this is finite, so I can just take the sum here. This is exactly the Riemann sum for this. So this term, now you have to write everything. I don't, because I'm on the board. So I just do big arrows. And this term converges as n goes to infinity to the integral from 0 to what? To t of df of dxk x, this is xi, so this is exactly your sampling. So this converges now to the continuous path x of s, b k x of s ds. Now this term here, this multiplied by this is exactly non-anticipating function multiplied by this. You go to the limit. This is exactly the definition of the stochastic integral. We'll get plus integration from 0 to t. So everything here has to be thought. You have to think about it as a limit. So you just take what we have been doing. This is, so I forgot this first sum. There is a first sum from k to little n, which is a dimension. And now there is another sum, which is the same, k from 1 to n. So this you have to repeat at home for yourself. ddf dxk x of s multiply by, so if we do it with the full notation. So this is a matrix sigma k q. This is a matrix, as we said. At position, I write it once, everything, and then you'll do it. D, and then we have to multiply by d omega of q. And here you have a sum. The sum for q from 1 to n. Right, because this is the matrix here. So I told you that this can be seen as a matrix sigma ij, and that you apply to this vector. So I just multiply everything. So it depends on k, on q, and this is the entire sum. All right? Now, as I said, there is a term that you will have to do it at home. But then there is be one term here that is going to be very important for us, because we know that what is the limit when we are going to get the product of d omega multiplied by d omega here. This, we have done it. We did it here. So let me rewrite this. We get, there is one more term that I'm going to rewrite, which is 1/2 of the sum from 1 to capital N of the sum of ddf dxi dxq dx k dxq. And then we have to be careful. So this term here, so this is a plus b multiplied by a plus b. So I take b multiplied by b. The rest I say I don't care because it will go to 0 when n goes to infinity. This is sigma. So this is k. So this is sigma k q multiplied by d omega I, and this is going to be, let's write it this way, d omega I q. And the same here, this is going to be sigma. So now this time we have, no, this q is not good, so let's call it q1. And this we have the q, so this is q, q2, d omega I. I mean, it's true that there is also, okay, I'll write it this way. And this multiplied by q2. And here we have to add. So there is a sum here on k, on q. And here I have added a term, which is the sum here on q1. And here a sum on q2, which I'll remove all the sum and put it there. The sum of q1 and comma q2. So I have 5 sums, but I don't care. What is the limit now of all of this? Don't care about the sum. When n goes to n goes to infinity, so this is the sum of the I. What is the limit of this? This is what we have done, what we just did, no?
The regular integral of
What is inside?
Yeah, it converges to what? So this is a sum of an infinite sum of Brownian variable. They are going to converge to the
mean.
That's right. What is the mean of this? You have to take the mean. That's right. So expectation of this, you have 2 Brownian variables. They are going to, everything will be cancelled except when they are all equals. That's right. And then when they are equals, it means that q1 equal q2. So this is sigma k q1, sigma k q1, d omega, this is going to be delta t. And then we are left with everything else. Nothing else has changed, which is going to be the sum for k, for q, and q1. We don't care about q2 because one sum drops. ddf dxk dxq, this. And now what is the infinity? I mean, I forgot something, which is the integral. Let me write it properly. This is the integral from 0 to t, capital T. This is ddf. I'm writing everything so that it becomes clear. dxk dxq. So sigma k1, sigma k1, y2k here. No, this is incorrect. This is q here. This is q. So this is k, and then we are left. So this is x of s at position s. This is x at position s. This is x at position s, and ds. And there was a factor 1/2. Are we good? I think so, no? And then we have to sum here over k, over q, and over k1. And actually over k1 you can have this over k1 here like this, over k1. And this is simply actually the matrix sigma, sigma transpose, which is here. If you do sigma, sigma transpose, this is exactly this matrix. That's why in probability, in the Ito equations, you get always this sigma transpose, sigma, sigma transpose that comes. And this is the equation. So what is the summary of all of this? Now we need to, this was for the case of the deterministic function. And now for the case, you can now differentiate everything with respect to capital T. So you don't have to write anything. Just write here d of f equals this plus this plus 1/2 of this, right? Because we have calculated here this quantity f of capital xt minus f of x0 equals this term plus this one. And this was the intermediate term. Right? 3 terms. And this is what in the PDEs will lead to the Laplacian and what you have seen when you study the diffusion equation, where it comes from. It comes from this formula, from the fact that here you have the second derivative. Okay, you have to redo it for yourself, for those who have never seen that. I wanted to do that for those of you who are not mathematicians, because this is how it is done. By understanding that this is a limit. You see this is a limit. And you replace basically, because we know that at the limit this is equal to the mean, so you replace by the mean. All right, so this is the df. This is the part that contributes to the other one, the time. It becomes linear with time, and this is becoming the stochastic term. All right, so I'll stop here. Next week, I would like to show how you use all of this to calculate mean first to write the equation for the mean first passage time, to write the Fokker-Planck equation, and then we'll be ready for some nice application that I have used, for example, to extract information from super resolution data. How you use this notion of expectation and conditional expectation to calculate how to extract mean, the drift and variance from data, from trajectory that you can acquire from your experimental data. All right, and then we'll do some conditioning so that you can see how you can calculate thin condition in the future. And then we'll be ready to go directly to the, I will skip some exercises and application, and we'll go for the exit problem. All right, see you next week.